For the task 1, we're gonna run this and then input the given input. We're gonna input the given numbers 1, 2, 3, 4, 4, 3, 2, 1. Enter. Uh, wait. I mean, so you can see, uh, for the input sequence, the value will be the input that you already stated, the 1, 2, 3, 4, 4, 3, 2, 1. For the magnitude response, it starts with 20. Wait, 20. Uh, this is 6. The 6.3, and then 0 point something. 4 I 0, and then 5, and then the fifth. And here is 6.3 again. And for the phase response, there's a negative 1. So it went 1, 2.7, 1.5, 1.9, 1.5, negative 1.9, and then it's 3.1, and then negative 2.7 something. And the IDFT sequence, this is also the same value as the one where you input. Starts with 0, 1 for the XY, and then 1, 2, 3, 4. And it's stated here for the 4, 5, 6, 7 that um, uh, the 4, 3, 2, 1 are the representations as a functions of frequency. Moreover, it's also represented by amplitude as its y-axis and phase. K as its x-axis. The answers are represented by a power spectrum that is repeated periodically. That's it.
So, good day. So, in here we will talk about linear convolution. So, for the task 2, so here's the code of the of the system. So, first, we will need to input enter first the first sequence and second sequence, and using convolution, so we will know the linear convolution of the system. So, after that, so we will grab the input sequence, the first sequence, the second sequence, and the convoluted output. So let's start. So the first sequence is the impulse sequence of 754 and 0. Then for the impulse response is 03629. So let's see the linear convolution. So the values are 0, 21, uh, 57, 56, 97, 53, and 36 and 0. So using MATLAB, so we can easily compute using the convolution conv function, and as you can see in the figure, that it represents the first sequence of 7, 5, 7, 5, 4, and 0. So as you can see in the amplitude, and for the second sequence, the impulse response of 0, 3, 6, 2, and 9. Yeah, this is 9. And for the convoluted output, so the convoluted system, the values is 0, 21, 56, 57, 97, 53, 36, and 0. So as you can see, the amplitude is where it is based of the values of the linear convolution. So as you can see that we can easily see the convoluted output in using the MATLAB. So, so it helps us know the relationship between the first sequence and the second sequence, and can greatly help understand the response of any input, and know and any input the system that can help me know the most efficient response in the system. That's all. Thank you.
In this video, we'll talk about the autocorrelation function of a ramp sequence for 0 is greater than or is less than n and less than 6. So what we'll do here is we'll input an array value containing all the numbers that is greater than 0 and less than 6. So those numbers are 1, 2, 3, 4, and 5. So as we can see in this given set of codes, first, of course, we'll do the close R and clear R functions. Then after which we'll enter an input sequence and then the subplotting and the display of functions with the usage of the xcore or the built-in xcore function from MATLAB. So without further ado, let's test our system. So again, we'll input an array value of 1, 2, 3, 4, and 5. So as we can see, the z values are 5, 14, 26, 40, 55, 40, 26, 14, and 5. So as we can see here, the input sequence is again 1, 2, 3, 4, and 5. And the autocorrelation input sequence will yield to a normal curve as seen in these plot lines. It's a normal curve. And our values here are displayed again, the 5, 14, 26, 40, 55, 40, 26, 14, and 5, and all the data types are double. So with that, we can see that the autocorrelation function works with the built-in function of MATLAB, which is the xcore. So that's all for the discussion of this item for the DSP final requirement.
So this is the task 4 for the final requirement in the Digital Signal Processing Laboratory, and it focuses on the frequency response or the influence of an amplifier output-input ratio on the signal that we have. It will also specify the frequency range that a component may replicate. So in this code, we can see that we're going to take the frequency response process from the input a and B. So, what is the input A and B? Input A and B is the numerator and denominator coefficients of the differential equation that we have. So, we should get that first. So, let's run the code. So, for the numerator coefficients, we have 1 and 2. For the denominator coefficients, we have 1, negative 3 over 4, and then 1 over 8. This is actually usable, especially for us students. So we can further use our understanding on how to obtain the normalized frequency response of a signal to construct the response of a circuit. So this is the output of the program, the output waveform. We can see the magnitude and the phase response. So for the workspace, we have the input A and B and the HW as well. So what's important about this? We can easily determine if the input variable can help amplify or diminish the signal and how the system can actually delay them. It can also actually help us graduating student in composting something for us artists, especially when displaying the frequency response of the hardware device that we're actually going to use, and to help that to solve problems that we encounter in the hardware.
For the task 5, let's run. Wait, let me get the input. One two one two three. Wait, 1 2 1 2 3. Let's paste the inputs and the sequence. 1 2 1 2 3 4 4 3. 1 2 1 2 3 4 4 3. Then as you can see here, the X is the input. The N will be 8. That means the number of the sequence or the numbers. For the XK, columns 25. Let's say that there also. Okay, let's try to open the. Let's add the capture. Right. As you can see, the input sequence will be the one who you inputted already. 1 2 1 2 3 4 4 3 for the magnitude response. The value of it is 20, 5.7, 1.4, 1.5, 2, exactly 2, 1.5, 1.4, and for the phase response, it started with 0, 2.05, negative 2.3, negative 2.5, 3.1, 2.5, 2.3, negative 2, and for the IFFT, it started with 1, 2, the same as the one you input. Okay, and then for this activity, the group is tasked to find the length of the input sequence using the length command. As you can, as it as it can be seen in this n, the n will be the one we're looking for, and then length command. The input sequence is the one we are inputted before we run the sequence, and xk are displayed in the command window with the different waveforms.
For item number 6 of the final requirement for DSP class, we will use the Google Colaboratory and Python programming language in order to achieve the objectives of the item. So first we'll have to install the pip for Spectrum, which has the requirements for NumPy, SciPy, Matplotlib, Python, PyParsing, Scikler, Kiwi Solver, and others. So with that, we will now actually import or load in this collaboratory notebook the necessary libraries that we will use, such as OS, NumPy, Spectrum again, and matplotlib.pyplot for our visualization. So next we'll have the actual finding or the locating of our OS path, which is the thinkdsp.python. It is a GitHub repository by Alan Downey, which also coincidentally has a book about DSP for Python. And now let's move on to the actual codes for the activity. So first, let's instantiate our variable n we could place any number here. For the purposes of this activity, let's have 1024. So the small letter n is dependent on the value of n, given that small n is np.arange, open and close parenthesis 0, comma, n minus 1, which is, of course, 1023. So now, for easier calling of the pi, we'll have np.pi is equal, or the pi is equal to np.pi, and then we'll instantiate our given function here, which is cosine 2 times pi times 50 times n. So with that, our array of values are ones, as we can see here. We could also actually use a.x.list in order to see all of the values for our x, but we're not going to do that here, it's tedious. So we'll now use periodogram in order to visualize and create our power spectrum. And using matplotlib, we will now have our visualization for power spectrum of our given function. So with that, that's all for this activity. And as we can see here, before we terminate this video, the values are forming somewhat of a curve here, given that our x value here will give this plot lines, or yes, plot lines for this activity. That's all. Thank you. This video aims to discuss and present the low-pass filter using Bartlett and Hamming window. So first, let's do the Hamming window. So to do that, we'll just use the MATLAB init or declared function, which is Hamming, then our value, which is in this case n plus 1, so that means 20 plus 1, so 21. So with that, we'll use it to instantiate all the other values, and let's try to demonstrate how we'll design a Hamming window for a low-pass FIR filter. So as we can see, which is you can see it, so this is a Hamming window for magnitude response of a low-pass FIR filter. So as you can see here, the magnitude response is somewhat like a sigmoid function or something like that, and our phase response is a zigzag line. So with that, let's look at our Bartlett or the triangle window. So first, let's clear all the commands and try to copy paste the original code and replace the Hamming with triangle. So it's also a built-in function on MATLAB, which is really convenient for this presentation's purposes. And as we can see here, the intervals between the points are much wider and higher than with the Hamming window. And also we can see that there is a more drastic increase or decrease in the values as compared to the Hamming window low-pass filter. So with that ends the discussion for item number 7 for this activity.
So this is the task 8 of the final requirements for the digital signal processing laboratory, and we're going to use here going to show here the high pass finite impulse response filter of the signal. So there are actually 5 windows available here, which are the rectangular, Bartlett, Hamming, and Blackman. So for this task, we're going to use the rectangular and the Hamming window. So the rectangular window is the most basic window, and they work by replacing all n values of a data sequence with 0, giving the waveform the appearance of being switched on and off. Well, the Hanning window is one of the windowing functions for smoothing data. It is also known as the tapering function or apodylation. So this is the code. This is where we're going to determine the window that we're actually using and to process them. So for the window, first the MATLAB command for the rectangular is boxcar, and then let's run it. There's no input number that the user actually have to enter, just in the code. So this is the output for the rectangular window. So from 0 to zero point 0.5 up to 1. And for the workspace, we have these values. And let's run the other window, which is the Hanning window. Let's replace the boxcar with Hanning. So this task actually gave us the students chance to practice implementing a non-recursive digital filter, and as we can see in this activity, it is a digital filter with a limited impulse response. So this is the magnitude response and this is the phase response of the Hanning window. And for the workspace, just brush this one. And this is the values that in the figure as well. And the magnitude response of the high pass FIR goes from a low to high value, as we can see in the figure, from 0 to 1 as always. And the actually we learned here the another type of window, which is the rectangular and Hanning of the high pass filter. And the low pass FIR phase response begin with a tiny gap between values and gradually increases in normalized frequency, unlike for this high pass filter.
For the lab 9, it is all about low pass filters using uh, the Chebyshev method. It is the one that is also used in the task 10, but in the task 10 it is all about high pass filter, and this task 9, what we're doing right now, is all about low pass filter. The filter or the technique or the method that we use in the laboratory is different from this, because in the laboratory it is the Butterworth method. This task gives us an idea to get the difference between the Chebyshev and the Butterworth method. That Chebyshev has a more specific and smooth phase response, as you can see in the figure, just like in the task 10. And when we run it, let's input the passband ripple, but the inputs we're gonna input here is the same input that we're going to that we inputted in our laboratory activity. And then let's show the difference between the two outputs from the laboratory and this. So let's see the difference between the Chebyshev and the Butterworth method. So the inputs are 15, 60, 15, maybe. Wait lang, let me check. So that there will be no 15, 3000 and 6000. 3000 and 6000. So here, let me show the capture MATLAB 2. Okay. So you can see this is the first graph is the magnitude response of an IR filter. The second graph is the phase response of the IR filter. So let me show the laboratory output. Window capture. Okay. So you can see here there are difference between those two. There are difference between those two, as you can see in the but Chevy Chev, there's only one down curve and then sudden up and then decreasing numbers here in the butterwork, in the laboratory activity. So you can see, so you can see the, so you can see it went up and down and then it flattens afterwards. That's all.
So good day. For the task 10, so we here to implement a high pass filter using Chebyshev method. So for the past lab activity, so we use a butterwork method. So now we use a Chebby method for short. So for Chebby method, so the difference between butterwork and Chebby method is that in the MATLAB, so you can see that in here, so the pass is butter one order. So here we'll use a Cheb one order function. So it's just the same function, and the inputs is the same. So the difference here is here. So in here, so the function that used for butterwork is butter. Here in Chebby we will use it is we will use Chebby one method using the input of the butterwork, but with a W1 or the WP, or the pass band of the uh, Chebby. So this is the new or the difference between the butterwork and the Chebby method. So here we need to apply the WP, or in here we will use the W1. So next is, so we will implement the pass band ripple, or so we will put 15. Then for the stop band ripple is 30, and for the pass band frequency is 1,500, and for the stop band frequency is 3,000, and for the sampling rate we will use 7,000. So it will be just the same as the lab experiment to know much more of the difference between them. So as you can see, so the magnetic response, if you can recall that the magnetic response in the butterwork is the same, as you can see, because it has the same input value, but also used, and the graph is also the same. So it's just so the main difference is in here in the pulse response IR filter, or the pulse response of the filter. So in here it has a smooth line covering it. So when the magnitude is in a high position, so here is it will go down. So that's the main difference between the butterwork method and the Chebyshev method. So Chebyshev filter uh, has a smooth and much more specific, because in the butterwork has the pace span is more like a heartbeat that has a rough edges, and so here in the pictures one it's much more smoother. So that's all for this is how to implement a high pass filter using Chebyshev method. So thank you.
In this video, we'll talk about the item 11 of the final requirement for DSP class school year 2021 to 2022 on the first semester. So first, as usual in the MATLAB, we will close all and clear our running functions. And then, as prescribed by the activity, we will instantiate p as 0 and 1. A as 1378, and the rest of these are from the previous laboratory reports. So let's first take a look on the value of x, which is instantiated as the formula for sine, open and close parentheses, t. So with that, we can see now where or what value will our visualization have, as seen on this visualization. So as we can see here, most of the values are of 0. So what variable or what number gives a 0 when we input it with sine? So sine, and you guessed it right, 0. So if the values for t is equal to 0, then x would also be 0 since x is sine t. So sine 0 is equal to t. And with that, we can see here that upon reaching x 5.7, the values actually now go up or go down. And as we can see on the topmost or the maximum value, it's around 6.2 with a y of 1.61, which is very far from the given values, which are zeros. So with that, that is the analysis for item number 11 of the DSP final requirement. Thank you.
So this is the task 12 of the final requirements for the digital signal processing laboratory, and here we're going to discuss and show the generation of the DTMF signals, or the dual tone multi-frequency signals. So the focus of the DTMT signal system is a signal system for detecting keys or dial digit on a push button. The combination of two sine wave tones create a key here. So it is a combination of two frequencies. And this is the code. So we're going to input the number, and we have a number 0 to 12, but actually it symbolizes these two symbols in the keypad that we actually have or known. So for that, the rows and columns values are then inputted based on the table, on the activity, and there is actually a table for the number and the corresponding frequency. And each values has equivalent formulate based on the table. It can be observed in the code establishing the input signal to represent each value on the y variables. So these are the y variables that we have, and this is the code. So for this task, we're going to input four numbers, which are the 5, 8, 3, and 12, or the hashtag. So let's run it. So first is the 3. Let's start with the lower value. So this is the output, and then let's run it again. 5. So as we can see here, the signals are more defined comparing to the 3. So let's run it again and input number 8. So this is the signal, the output signal or waveform. Then lastly, let's input number 12, or the hashtag symbol. And this is the workspace showing all of the values that we have in the system or in the signal. So comparing all the program outputs, a higher input number produces a more messy and convoluted output signal. Like for example, for this 12, we can see the signal is not that good and more convoluted comparing to what we have in input number 3 and 4. So here the student successfully replicated the generation of a dual tone multi-frequency signal in the task, and it is one of the actual foundation for voice communication control and frequency utilized in modern telecommunication. We can employ this knowledge regarding the sinusoidal frequency as mentioned in the previous discussion in the course.
So good day. So here for the task 13, we'll do a decimation of the signal. So it will downsample the signal. So first in the code, so as you can see, for the decimation process, we need a down sampling factor and the length of the input signal. And here for the problem, so we will use the uh, equation of cosine. Then the inside of it is 2 times pi times 30 times the n, or the length of the signal. So let's do it. So for the downsampling factor, so we will use the downsampling factor of from the last lab experiment, that is 5. Then for the length of the input signal will be 100. So as you can see in uh, the graph, so this is the input signal of the cosine. So here we can see that this is the original input sequence of the, or the sampling rate. That here is the decimated sequence. So we can see the difference of it, that it only decimate the sampling signal to for every 5 of the input sequence of the signal. So that's why it is important to do the decimated sequence to help stabilize the signal and cut all the unnecessary information. And also in this task or lab or the problem, so it can help us to do any input sequence that is needed to do a dissemination, to help or learn more about that help us to learn more about dissemination using the MATLAB and how greatly affects it in the structure of the signal. So that's all. Thank you.
So this is the task 14 of the final requirement for the digital signal processing laboratory, and here we can use and we will show the interpolation process in the input signal that we have. So we're going to take for input from the user, which are the upsampling factor, the length of the signal, which should be greater than 8, and the frequency of the first and the second sinusoidal signal. And for the direction, specific direction, we're going to use the x input cosine 2 times pi times 3 times n. We're going to run the code. So for the upsampling factor, we're just going to use the last input for the laboratory similar to this, which are the 5, the 9, like should be greater than 8, and then 0.1, and lastly 0.3. And this is the output waveform, and it show the input sequence and the output sequence. So we have the input sequence, the amplitude, and as we can see here, there are 45 lines in the output sequence and many data points. And the x-axis represent or display the length of the input signal, which is 50, and increasing the values of the two sinusoidal frequency resulted in more dispersed waveform in the output sequence and the output in the input and output sequence, as well as precise and complete signal sequence. For the workspace, we have these values in the signal, the F1, F2, LM, N, and RX. And as conclusion for this task, the interpolation or upsampling procedure followed by filtering is the center or the thing that we show. This procedure employs an sampling technique in which the sampling rate of the program is increased, as we can see from the input and the output sequence. Interpolation is the reverse of the precision that conducted in task 13 and can be used in many standards to read more special sample rates to improve the comprehension of graphs. It allows also us the students to modify the input to understand better on how various input can affect to the output signal that we have. And the X input is also similar to what we have in task 13 and task 15 of this final requirement.
So, good day again. So, in the task 15, we will do a multi-rate sampling method. So, in here, first, we need to do the upload sampling factor or get a upload sampling factor. The next is the downsampling factor of the signal, and next is lastly the length of the signal. So, in here, we will use the equation of cosine 2 times pi times 30 times n for the x value. So then using that, so we will do the multi-rate sampling. So let's go. So for the up sampling factor, we will use 10. And for the down sampling factor, we'll use 20. Lastly, the length of the input signal, we will use 100. So now, as you can see the graph, so here is the output sequence and also the input sequence of the signal to know the changes or what happened to the signal. So here we can see the input signal that has the original sampling factor or the sampling sequence. Next is the output sequence. So here, for the process of multi-rate, the first method or the process will be the upsampling. So it will upsample the signal, then downsampling it. So, and here is the output signal. So it becomes like that. So like a only downsampling method because the downsample has more factors than the upsampling or greater than the upsampling factor. That's why it is more look like a downsampling method. But that's the process of the multi-rate sampling methods, and that's all. Thank you.
For the lab 9, uh, for the task 16, let's run. For the B, the values are 0 and 0.5, and for A, 1 and 5. So, and then plot, and then second order system for the values of B is 0, 2, 0.5, and for A is 4, 5, and 1. and then plot again. So let's run. As you can see, for the impulse response of first order system, here 1, 1 and 0.5, 2 and negative 2.5, 4 and 6. As you can see, the end for the amplitude it stays at 0, and then at 9 it went up to 1, and then for the impulse response of second order system, 1 and 0.5 started at 0 0, 2 and negative 0.5, then it alternates up to the 10.